Today I want to talk some about inverse trig functions. We've talked about inverse functions a number of times. Back when we were talking about just straight line functions, we saw how we could calculate formulas for the inverse function. When we talked about logarithms and exponentials, we studied the exponentials first, then constructed the inverse functions and called those the logarithm functions. We'll do the same here. I'll think about the graph of y equals sine x. I'll interchange the x and the y to get x equals sine y, whose graph has the same points as the graph of y equals sine x, except since x and y have been interchanged, things that used to be horizontal are now vertical, and things that used to be vertical are now horizontal. So the equation x equals sine y has this for a graph. This is not good news. This fails the vertical line test. This is not the graph of a function. We had a similar situation when we were looking at y equals x squared versus x equal y squared. The way we'll fix our sine problem is the same way we fixed the square root problem. I need a chunk of the sine of x graph that produces all conceivable sine values from -1 to +1, but only produces each sine value exactly one time. So what we do is, instead of looking at the entire graph of the sine function, we'll only look at it from -pi/2 to +pi/2 radians, or if you like degrees better, -90 degrees to +90 degrees. If I take just this chunk of the sine graph and look at its inverse, we avoid the repeated function value problem. This is a function. We're going to call the name of this function arcsine, or more confusingly, inverse sine. And you must understand that when we're talking about inverse sine, this is not 1 over sine. It's the inverse function instead. So we'll just name this arcsine for now. The domain of the arcsine function is all of the x values that you can put into it and produce an output. So the domain of the arcsine function is -1 to +1. The range of the arcsine function is the collection of all the y values on its graph. And on the graph of the arcsine function, y could be as small as -pi/2 radians, or as big as +pi/2 radians. Inverse sine of 2 doesn't make any sense. 2 would be here, and there is no point on the graph to go with x equal 2. If you are outside the range of -90 degrees to +90 degrees, or -pi/2 to +pi/2 radians, then the angle that you're looking at is not a value of arcsine because of the range of arcsine. In a perfect world, f of f inverse of x is x always, and f inverse of f of x is x always. But considering the fact that we have restrictions on what kind of x's we can feed either into the chunk of the sine function we're using or into the arcsine function that we've just cooked up, things are not quite so simple. If you think about sine of inverse sine of x, inverse sine of x only makes sense if x is between -1 and +1. So if I calculate inverse sine of x, and then feed that into the sine function, I should get x back for an answer if the x that I started with is not a troublemaker, if the x that I started with is between -1 and +1. Outside of that range of x values, sine of inverse sine of x doesn't even make any sense because inverse sine x doesn't make any sense. I have my calculator set in radian mode here. So I want to draw the graph of y equals sine of inverse sine of x. I get the inverse sine function by saying second sine of inverse sine of x, close parentheses, close parentheses. I'll put this on the standard viewing window to start with. And you'll notice we just get a very small piece of graph. Let me zoom in on that a little bit. It looks like what we figured it was going to look like. It looks like a straight line. Possibly it's a chunk of y equal x, and beyond x equal 1 and before x equal -1, I'm not getting a picture. To convince myself that this is right, I'm going to draw this graph again in a minute, but I'm also going to draw the graph of y equal x. If sine of inverse sine of x is x, then the two graphs ought to be on top of each other, at least for the x's where both of them make sense. So I'm going to go into my y equals menu, and in addition to sine of inverse sine of x, I'm just going to draw the straight line y equal x. And we know what's supposed to happen. That little chunk of straight line that we saw before should be part of this straight line that we're drawing now. And as you can see, that's correct. So sine of inverse sine of x is x as long as x is between -1 and +1. Outside that range, you don't even get a value for sine of inverse sine of x. Inverse sine of x is trickier. If you give me any x number, I can calculate its sine value, and I'll get a number that's between -1 and +1. That's a number that I can feed into inverse sine function. So inverse sine of x always makes sense. But on the other hand, it can't always be x because inverse sine can only produce results that are between -π/2 and +π/2. So I've got a prediction. I predict that inverse sine of x is going to be x for certain x values, but not others. And outside that range of x values, namely -π/2 to +π/2, it will exist, it will be something, but it won't be x. So we'll do as before. I'm going to have y1 being the inverse sine of the sine of x. I'll draw its picture on the standard viewing window, and then we can zoom in if we need to. Zoom 6. So the graph appears to be straight line segments, except they keep changing direction as you go from one chunk of the x-axis to another. Let's zoom in. The reason I want to look at this piece in the middle is the part where x goes from negative pi over 2 to positive pi over 2 radians is allegedly the set of x values where my inverse sine of x is going to be x. So I'll graphically verify that by drawing the graph of x in. We know what's supposed to happen. In the appropriate range of x values, this should lie right on top of that other graph, but obviously not others. And you can see what we expected to happen does in fact happen. So sometimes you have to be very careful about domains and ranges of functions and their inverse functions. Sometimes because of the kind of restrictions that we've put on, you have to be more careful than usual. If we look at the tangent function, whose graph I've drawn here, the graph of y equal tangent of x, you'll call this has an infinite number of vertical asymptotes, as they're called, places where the graph basically goes vertical on you. When I interchange the x and the y, that means there's an infinite number of horizontal asymptotes. So when I look at the original y equal tangent of x, interchange the x and the y to get x equal tangent y, again, things that were vertical become horizontal and vice versa. X equal tangent y looks like this. And clearly, this fails the vertical line test. Draw any vertical line, and it touches x equal tangent of y an infinite number of times. The way we're going to fix this up is the same way that we fixed it up for the sine function. We have the same issue as before. I need to have a chunk of the graph of the tangent function that produces all values that the tangent function can produce and doesn't have any repeats. If you look at the previous page and think about that graph, one thing that I could do would be look at all of the x values that are strictly between negative pi over 2 and pi over 2. This will produce all of the values of the tangent function and will not have any repeats associated with it. If you take that and interchange the x and the y so that x is tangent y now, this chunk, when you flip it over, gives you this picture. The name of this function is the arctan function, or inverse tan, as your calculator has it. The domain of the inverse tan function is everything. No matter what x you pick, there's a point on the graph of the inverse tan function to go with it, but the range is restricted. The range goes between negative pi over 2 and positive pi over 2, and this time you can't even get the pi over 2 and negative pi over 2. On the graph of the tangent function, there is no place where x is pi over 2. So on the inverse function, there's no place where the y is tangent, where the y is equal to pi over 2. You can make the y coordinate as close to pi over 2 as you like, but you can't actually make it equal to pi over 2. Not to repeat ourselves too much, we'll just do some calculator experiments. Let's look at what y equals the tangent of the inverse tangent of x looks like. Well, let's make a prediction first. Inverse tangent of x makes sense no matter what x is. Tangent of inverse tangent of x can't always be x because the inverse tan can't give you an answer bigger than pi over 2, for instance. So what I expect to see is a chunk that looks like y equal x and then other things. We'll put this on the standard viewing window to start with. Well, I misspoke. It's the other one that's going to cause trouble. Tangent of inverse tangent of x, looking at our experiment here, actually does look like x everywhere. Let's see what the other one looks like. Let's look at inverse tan of x. Yes, I misspoke on the previous one. The trouble here is going to be because inverse tan can't produce just any old number as an output. It can only produce answers between negative pi over 2 and positive pi over 2. So let's draw the graph of that. And you see, this is the one that's the troublemaker. As a sanity check, we'll also draw the graph of y equal x. And you see that central part is a chunk of y equal x, but number one, it's not the whole line y equal x, and number two, things outside that particular range of x values don't give you back x, they give you back other things. Also worth mentioning is, if you calculate the inverse sine of something, you're going to get an angle out of it. This angle could be anything from negative 90 degrees all the way to positive 90 degrees. So inverse sine of something will never give you an angle that's over in the third or fourth quadrant. And the same comment is true for the tangent function, except this time you can't even get the negative 90 degrees, negative pi over 2 radians. You can get as close as you like. You can get bigger angles. You can get angles that are almost 90 degrees. But if somebody walked up to you and said, you've got this angle theta, and they started to say that theta is the inverse tan of something, that's wrong. It's automatically wrong. Inverse tangent can only give you back these angles. Inverse sine, similarly. So if you have pictures like this, and somebody says that theta is inverse sine of something, or theta is inverse tan of something, if you understand about these inverse functions, you look at it and you say, that's not right, that's incorrect. Suppose you wanted to solve the equation sine of theta equals 1/3, and you were only looking for answers that were between 0 and 2 pi. What you can do is you can draw the unit circle, and you remember the sine of theta on the unit circle is the y coordinate. So you're looking for points on the unit circle that have y coordinate equal to 1/3. So one such angle will be there, and another such angle will be there. If you look at the angles separately, this angle is between negative pi over 2 and positive pi over 2. Because of what we said about the arcsine function, that angle, the one that's in the first quadrant, it must be arcsine of 1/3. And this one, if you think as we have previously, starting here on the positive x-axis, if you went all the way to here, that would be pi radians. But you haven't quite gone that far. You are short by this amount, which we've said previously is the same as this amount. So this angle is pi minus whatever arcsine of 1/3 is. So I claim that in the range of angles from 0 to 2 pi, there's only two angles that make sine of theta equal to 1/3, and there they are. Let's do a sanity check. Firstly, and almost insultingly, I'm going to calculate the inverse sine of 1/3, and I'm going to store this into a variable in the calculator. I'll store it into what the calculator calls the x variable. Then I'm going to calculate sine of that x value, and I get 1/3 like I'm supposed to. Even if we only half understand the inverse function stuff, that shouldn't come as a surprise to anyone. What should, though, is I'm going to take pi radians minus the arcsine of 1/3 and calculate that angle. I'll store that into a variable also, and then I'm going to calculate sine of that value, and I get 1/3 back for an answer again. This convinces me that this is right. I have found these two angles between 0 and 2 pi radians where sine of theta is equal to 1/3. Since the range of the inverse sine function and the range of the inverse tangent function are practically the same thing, the manipulations that you would do for the inverse tangent are practically the same also. So in the interest of brevity, I'll omit that. And think about the cosine function. The graph of the cosine function, as we've seen previously, is a wave, very much like the sine function, except at x equals 0, the cosine function is 1, and at pi over 2 and negative pi over 2, it's 0. If you try to use the same range of x values on the cosine that you did on the sine and the tangent, it doesn't work. If I take this piece of the cosine graph, y equal cosine x, and flip it so that x is cosine y, this part becomes this part, and it's no good. This attempt fails the vertical line test, so this is no good. It's not the graph of a function. The problem is that if I center my x range on the cosine function at 0, I'm automatically going to get repeated function values because cosine is an even function. I need a set of x values for the cosine function that produces all values that cosine can produce, but only produces them once. So what we're going to do is not go from some negative number to the negative of that number. We're going to start at 0, where the cosine is 1. We're going to move to the right until we get to pi radians, where cosine is negative 1. If you proceed any further to the right than that, you're going to begin getting function values that you've seen before, which will mess up your inverse function. So we're going to use this chunk. We're going to start at x equals 0, and we're going to end at x equal pi. This is going to be the chunk that we use to construct the inverse cosine function. Using only that chunk, y equal cosine x, interchange the x and the y so that you get x equal cosine y. This point, where x was 0 and y is 1, gets turned into x equal 1, y equals 0. This point, where x was pi and y was negative 1, gets turned into x equal negative 1, y equal pi. There was a point on the x-axis with coordinate pi over 2, so there'll be a point on the y-axis with coordinate pi over 2. That passes the vertical line test, so it's a function. We'll call the name of that function inverse cosine or arc cosine. Also, it's very convenient at times this cosine, inverse cosine business, the numbers that come out of the inverse cosine function are between 0 and pi radians. That's 0 to 180 degrees. Those are the kind of angles that you could get out of a triangle. So dealing with triangles, the inverse cosine function could be very convenient for us. For an example, in a triangle, if you knew that the cosine of some angle was 0.2 and wanted to know what the theta was, because of what we just said a moment ago, theta has to be inverse cosine of 0.2, which works out to be a little bit more than 78.46 degrees. In a triangle, there's only one angle that will work. That is a different question from these two questions. A, find all theta in the interval from 0 degrees to 360 degrees, where cosine of theta is 0.2. B, find all real numbers theta so that cosine of theta is 0.2. I decided to go back to using degrees just for variety. On the unit circle, the cosine of theta is the x-coordinate. So I'm looking for points on the unit circle that have x-coordinate equal to 0.2. And obviously, there's going to be two of those. One of them is there, and the other one is there. One of these two angles is in the range 0 degrees to 180 degrees. That's where it's safe to just use the inverse cosine function and get your answer. So as we saw before, this angle is inverse cosine of 0.2, which is 78.46 degrees. On the other hand, there's the angle that has terminal side here. There's various ways you can think about doing this. If you started on the positive x-axis and went all the way around, that would be 360 degrees. You didn't quite go that far, though. You are short by this amount, which is the same as that amount. So this angle is 360 degrees minus inverse cosine of 0.2, which works out to be 281.53 degrees approximately. Now, I've reset my calculator into degree mode because that's what I'm doing here. I want to calculate 360, that's in degrees now, minus the inverse cosine of 0.2, and this gives me my 281.5 degree angle. To keep from having to type the digits again, I'm going to store that into the x variable. Allegedly, cosine of that angle is 0.2. Oh, excuse me. Cosine of that angle is 0.2. This was an obvious insufficient caffeine moment there. But anyway, the cosine of 281.536959 degrees does work out to be 0.2, as it should. So we actually have found both of the two angles in the range 0 to 360 that will give cosine of that angle equal 0.2. The second question was, find all real number solutions of cosine theta equal to 0.2. Well, we have determined that there's two of these in the interval from 0 to 360 degrees. If you find one of them, you could imagine doing this. Construct that angle and then go completely around another 360 degrees. and it will put you back at where you were a moment ago, and cosine will still be 0.2. You could make your angle go completely around in a circle, go completely around another circle, and that will also end you up where you're at before. Cosine will still be 0.2. You could form your angle and then subtract 360 degrees from it, and you would end up at the same terminal side, so cosine would still be 0.2. So if I have one angle that will work, then anything that looks like theta plus 360 times a whole number will also work. To finish answering question B, previously we saw that there's two angles in 0 to 360 that will make the cosine equal to 0.2, and these are the two angles. If I take that first one and add a whole number times 360 to it, I get the arc cosine of 0.2 plus 360 times n, where n is short for integer. It's a whole number, could be positive, could be negative, could be 0. Also, 360 minus arc cosine of 0.2 plus a whole number times 360 will also work. I'm just going to call 1 plus little m capital M. The other collection of solutions is going to be a whole number times 360 degrees minus arc cosine of 0.2. So not only do I have an infinite number of solutions to cosine of theta equals 0.2, I have kind of a doubly infinite set of solutions. Some of them basically come from that one, and the other ones come from that one. But we have now found all real numbers theta, so the cosine of theta is 0.2. As one last sanity check, I want to draw the graphs of inverse sine, inverse cosine, and inverse tangent, and make sure they look like what we think they look like. So I'm going to go into my y equals menu. I'll get rid of all this old stuff. I want to draw the graph of inverse sine of x. And as always, I'll check my mode. I've decided to go back to radians here. So I'm going to put this on the standard viewing window, and it's a little hard to see, so we'll zoom in. This is what we figured the graph of the inverse sine should look like. The x numbers can be between -1 and +1, and the y numbers go from -π/2 radians to +π/2, and π/2 is about 1.57. What about the inverse tangent? So we'll just look at its graph as well. This is what we figured it looked like. Let me do a sanity check on those asymptotes, though. We'll draw some more stuff in. I'll draw in the constant y equal pi divided by 2 and y equals negative pi divided by 2. On this chunk of the graph, I think it's pretty obvious that as you move off to the right, the y coordinate on the graph, the actual arctan value, gets close to pi/2, and as you move off to the left, it gets close to negative pi/2. If you put this on the standard viewing window, it's much less informative, though. My calculator's had some sort of nervous breakdown. If you put this on the standard viewing window, the pixels get so squished together it's hard to see anything. But that's all right. We've figured out logically what the graph actually looks like. And in our zoomed in picture, where things aren't quite so squished together, we see that things are the way they should be. And lastly, I want to look at the graph of the inverse cosine function, but logically speaking, there's not really any need to do this. We've figured out what it has to look like, but we'll do it anyway. Inverse cosine of x, standard viewing window to start with. As before, it's difficult to see, so we'll zoom in. We see that the shape appears correct. I have a negative x coordinate and a positive y coordinate. I'm not entirely sure about my window settings. Let me see how I'm doing here. Ymin and Ymax, the Ymax is a little short. I want to make Ymax at least as big as pi so that I can see the top of my graph. Pi is about 3.14, so I'll make Ymax a little bigger than that. I'll make it equal to 4. There we go. I want to do the trace thing, second trace, and I want to put in -1 for the x. It had problems with it. Well, trace -1 for the x. There we go. When x is -1, y is 3.1415, which is pi. That's what it's supposed to be. When x is 0, the y coordinate's supposed to be half of pi, which is about 1.57. So I'll put x equals 0 into the inverse cosine function, and we get 1.57 some odd. When x is 1, y is supposed to be 0, and that's what we see. So the general shape of the thing is correct. These points that we in particular identified are correct. This is the correct graph of the inverse cosine function. This has been a brief summary of the essentials of inverse trig functions. I believe this will be enough to get the job done. We will talk about another topic in the next meeting.